Homework questions. Or just questions from me in general about anything. So just as a note, I realized that I had some wrong dates on the homework because, like last time, since our exam falls on a Monday, we are not going to be yeah. Since our exam falls on a Monday, we are not going to be having a quiz this week. And so if we're not having a quiz this week, that means there's no homework due this week. So all of the homework that was going to be due on Wednesday has been pushed back to Monday. So all of the chapter 6 stuff as well as the chapter 7 stuff, which we're going to catch up and finish this week, that is going to be due all next Monday, which is going to be our next exam date. So once again, I will be posting a study guide just like I did last time. I will also will be reviewing on Wednesday, covering stuff about the exam and all that sort of stuff. Any questions on that?
So, exam is next Monday?
Correct. A week from today.
Okay, just checking.
Anybody else?
And no quiz Thursday?
Correct. We will not be having a quiz this week because I don't like I said there will be time like I don't see the point of quizzing you on Thursday and then having an exam the following Monday. That doesn't make sense to me. So in lieu of a quiz this week, we're going to have our exam right when we come back next Monday after the weekend.
Okay, so next Monday is.
And yeah, like just like last time, I'll be posting a study guide to the files. I'm almost done with it. I just gotta I need to write up the solutions for it. I haven't done that yet. So I'll be posting those up in the next 24 hours. And on Wednesday, we'll be reviewing for the exam. Yeah. Okay. Any other questions before we get going? Alrighty. So in that case, we're gonna move. We're gonna go back into chapter 7. With what we call complex fractions. And really what we mean by complex fractions is just fractions that contain fractions. So numerically, this would look like something like, something like that. And we're going to have I'll kind of show you the two methods numerically we have to work this out. Actually, you know what, let me make that about 1/5. And there are kind of two methods to work this one out. The first being we just kind of treat this as a top and a bottom separately. So on the bottom, we're just going to have something like 1/5. And then up top, what we're looking for is anytime we need to add, we're going to need some sort of LCD. So I would do a thing where I put this over 1. And then my LCD here would be 2. So I would hit this with a times 2/2. So that'd leave me with 1/2 plus 6/2, which would give me 7/2 all over 1/5. And then in terms of multiplying, or how do we work this out is, well, we multiply by the reciprocal. So this would be 7/2 times 5/1 or just as a fraction, 35/2. So this would be a method where we find kind of a top and bottom LCD separately, and then proceed to kind of work out as needed. The other way you can kind of work this out, which is we talk about 1/2 plus 3 all over 1/5, is instead of looking at this as the top and bottom as two separate pieces, we find like a global LCD. And once we find that global LCD, we can use that to take care of all of these fractions more or less at the same time. So what that would look like here in this case would be, well, we have a global LCD. If we look at all of my fractions, so here we've got technically a fraction of 2. This is technically over 1. And this is over 5. If we look at the LCD of all three of those, well, that would just be 10. So what we're going to do is just kind of like what we did here for the single fraction, we're going to do for this entire fraction, which is we're going to multiply this by 10 over 10. And why that's helpful to us is kind of like when we're working with fractions, as we multiply this through, if we look here, 1/5 times 10, well, 10 divided by 5 will cancel out and leave with a factor of 2. So we just have 2 in the denominator. And then as we kind of multiply this out, right? We're multiplying a 10 on both pieces here. So we have a 10 here and a 10 here. 10 times 1/2, once again, we cancel out. Here we're left with a 5. So 5 times 1 just gives us 5. And on this other one, nothing cancels. So 10 divided by 1 is just 10. 3 times 10 gives us plus 30. So we end up, once again, we end up with the exact same goal, or the exact same final answer, I should say, which is 35/2. I show you both of these. Honestly and truly, I think there are kind of versions where maybe one's a little bit easier than the other. But if one makes way more sense than the other one, stick with that. Some people really like doing this kind of like, I work with the top and bottom as two separate pieces and then just divide at the end. Some people like I do a one big LCD for everything and then cancel that out. It's technically about the same amount of work. It's just which one do you actually prefer using? And that's really all there is to it. There's not much more to it than that. And for the most part, what this really is just more, it is not that we're learning a new technique, it's really just applying the techniques we already have to a slightly more complicated equation. So I'm going to give you an example where we work out, where I'll kind of give you one where doing it versus a top and bottom is a little bit easier, and finding a global LCD is a little bit easier. So let's just kind of, and once again, the prompt for all of these is to just simplify. So let's look at this one. So the first thing we want to do is you always want to factor everything down, right? So we have all these denominators here. We always want to make sure that all of those are factored down, and these first two are already factored down. We can do a quick little factoring at the difference of squares. So we're left with 2 all over x plus 6 all over 4 over x minus 5 plus 2 all over. So difference of squares means that's going to factor into x plus 5, x minus 5. Okay, so now whether we want to look at this as a global thing where we find one LCD for everything, or we want to work this out as a top versus bottom. Now, if we did find a global LCD, we'd have to have 3 pieces, right? We'd have to have an x plus 6, an x plus 5, and an x minus 5. And then what we'd have to do with that is take that LCD and multiply everything on top and everything on bottom by that global LCD, which once again, doable, a lot of stuff cancels, but there's a lot of stuff that doesn't, and we'd be left with a lot of algebra that's left over. So in this case, since our LCD for everything is kind of messy because there's not a lot of common ground in between these guys, I think it's actually easier in this case to work with just top and bottom by itself. Reason for that is a couple things, which is one, if we do deal with top and bottom, the top's already a single fractions, the top's already done. Like we can just write this as 2 all over x plus 6. And then on the denominator, instead of looking at the whole thing, we're just looking for an LCD here, which would just be x plus 5, x minus 5. And that is going to be, well, what we multiply on this first term, which is we have the x minus 5 already, but we need to multiply by is x plus 5. So if we multiply across, it's going to give me, as we distribute, 4x plus 20 over x plus 5, x minus 5 plus 2. All over. I'm going to scoop this over just a little bit. All right. So we do our LCD work, and now we've got a common denominator on that bottom piece, so we're just going to add that together. And then all over, so we'll just have 4x plus 22 all over x plus 5, x minus 5. So remembering that when we divide, these are technically 2 fractions, we just multiply by the reciprocal. So this is going to be multiplied by x plus 5, x minus 5, all over 4x plus 22. Okay, so decent. I mean, once again, there's no version of this where there's not a decent chunk of work, period. But for the most part, all we really did here was just add that denominator up, and now we're just dealing with the results of this division using the reciprocal. So technically, we're just doing just the 2 pieces we did last week, which is division and addition, and we're combining them into one problem. So, like we covered last week, we always want to be looking to factor and cancel. So a lot of this stuff in here is already factored. So 2 over x plus 6, can't do that. X minus 5, pardon me, that should have been x plus 5, is already canceled. Or sorry, factored, I should say. And last step, we can pull a 2 out of this. And that's just nice, because that'll cancel out. And we're done. Up top, we have x plus 5, x minus 5. And on bottom, remember put parentheses around that, we have x plus 6 to x plus 11. Alrighty. Questions on this? Anybody? I'll go a second, kind of write that down. Because like I said, these do require a decent chunk of work. So there's no getting around that. But really all we're looking to do, and if we're doing breaking up as top and bottom, we just do LCDs of top and bottom, work those out, and then at the end we just apply the division by multiplying by the reciprocal and just canceling out where appropriate. Okay, excuse me. Questions? Anybody? So I didn't formally say this, but this is technically looking at, we look at the top and bottom separate. Whereas the other version, we have something like this. For reasons you'll see in just 1 second, I think this one actually makes a little more sense to find a global LCD. And the reason for that, once again, we want to put this, we'll color code this. Putting that over 1, we have a pretty easy LCD here, which is, remember, LCD is just the highest power. So since we've all got powers of x, my global LCD is just going to be x cubed. So what that means is we're just going to multiply, once again, if we're treating this as a global LCD, top and bottom by this x cubed. So just kind of writing out what that looks like. So we're just going to take each one of my terms and just multiply this by an x cubed. And if we did our work right, a lot of these should be either very simple multiplications or we should get a little bit of cancel. Here, we have no denominator, so we're just going to multiply them together. So that's going to give me 14x to the 4th plus here, x squared will cancel and leave me with x, so we'll have plus 5x. In the denominator, this will cancel out and leave me with an x squared. So that's going to be plus positive, I should say, 3x squared. And then here the cube just cancel out, and we're just left with plus 4. So general rule of thumb is if you have a simple LCD, if you have an LCD that's one term, I think it's usually a little bit easier to find a global LCD, multiply through, and then just simplify down. Whereas if you have an LCD globally that has more than one term in it, I would say that's usually where it's a little bit easier to work with the top and bottom separately. Okay. Are there any questions on this? Ready, let's look at one more. Okay. So once again, looking at all of this, we see we have a lot of powers of x and powers of y. But because we're just dealing with powers, the LCD is going to be pretty simple if we look at a global LCD. Which is we're just going to take the highest power we see of both, and the highest power we see of both is an x cubed and a y cubed. So now all this means is we're going to multiply top and bottom by this expression. So actually move this down just a little bit. What that means is every term is going to get multiplied through by an x cubed, y cubed. And we're just going to go through and do mostly just a bunch of canceling. So if we look, kind of go through here, so we got to be careful here. The squared cancels and that'll leave us with a y. So first multiplication is going to be 64 x cubed y. Minus. Here we're going to have the x squareds cancel. The x squared will cancel with that. That's going to leave me minus 27x y cubed all over. And then if we look to see what we have kind of at the bottom, here we're going to have a lot of stuff cancel out. We're going to get the x, well, the y cubes cancel entirely. And the squareds will cancel, so that'll just leave me with 4x. And then here, the x cubes cancels entirely, and we're going to have a y left over, so minus 3y. Okay, question so far?
Would you mind going up a little bit?
Sure.
Just a little bit. Yeah, stop right there. Good. Thank you.
Okay. Okay, and then if we look to kind of cancel out here, if we're looking to factor, denominator is already factored. And then we can kind of see, if we look and see what both have in common, both have an x and a y attached to them, so we can factor out an xy. And if I do, that's going to leave me with, what's that, 64 x squared minus 27 y squared, which almost looks like a difference of squares, but the problem is that 27 is not a perfect square. So we can't really do, like, technically factor out the xy, but nothing cancels out here. So we're kind of just here with the final term as it is. Okay. Questions on this, anybody? Alrighty. So that's kind of the end of the like technique stuff, kind of setting up how to work the algebra on these. In our next section, 7.4, we're actually going to use all these techniques to solve rational equations. Which technically we've already done. We've done, the technique we're doing is one we've done before by something like this. Where we've got all these fractions. We had a technique for solving this without having to deal with a bunch of fractions, and that was to find our LCD. And if you look here, the LCD of 2, 3, and 5 happens to be, sorry, not 15, pardon me, 30. And all we're going to do is just take that, and what we did is just multiply that through. So we're going to take everything through and multiply it by a 30. And we just kind of cancel out, right? 30 over 2 is 5, so we're going to be left with 5x. 30 divided by 3 is 10, and 10 times 2 is going to give me minus 20. And then on the right-hand side, 30 divided by 5 is 6. And so we'll just have equals 6 here on the right-hand side. All right, so now we're just solving, right? Add over the 20. So 5x equals 26, and then if we divide through by a 5, we get our value, x equals 26. Questions on that, anybody? So this is where we work through. Now what we're going to do is just look at that, but with some slightly more complicated expressions. So one thing we've been looking at is we've been looking at things that have a variable in the denominator. So something like 2. The same thing, it's still going to be the same thing, which is solve 3x plus 4 all over 3x minus 1 is equal to 1 all over 2x. And it looks kind of daunting, but for the most part, we're going to be treating this in the exact same method as we did last time, which is we're just going to kind of find an LCD, multiply through, and cancel out. And what we're left with will just be a expression that we can solve. So, in terms of the LCD, once again, looking at this, since these are not multiples of one another, there's no way to multiply a 2x. You can get a 2x to a 3x, but you can't get that minus 1 in there. That means that my LCD in this case is going to be 2x times 3x minus 1. So just like we did in the last problem, what we're going to do is we're going to cancel out all of these denominators by multiplying through my LCD. So the full LCD of 2x times 3x minus 1 and 2x times 3x minus 1. And once again, just like last time, the reason why we multiply through is that this is going to cancel out the denominators. So we've got those cancel. And so what we have left over is a 2x times 3x plus 4. And then on the right-hand side, the 2x's cancel. And we're technically left with a 1 times 3x minus 1. All right, so as we multiply through, once again, doing our work here, pardon me, that's 6x squared plus 8x is equal to 3x minus 1. Okay, so working this out. So this is some work we did last week. We have a polynomial because I've got x squareds and x's, so I've got two variables. I'm going to ask about the last question. I apologize. Yeah, I stand correct. Yeah, that should have been, you're right. I can't do, yeah, 30 over 2 should be a 15. So just put some ones there. I forgot to write, pardon me, I forgot to write my fraction here. Excuse me. Sorry about that. So yeah, continuing this one out, we have a polynomial with differing terms. So remember the general rule of thumb is we're going to set it equal to 0 and factor. That's how we solve these. So once again, you can subtract over either way. I like to keep my highest power positive, which means what I'm going to do is I'm going to subtract over a 3x and a 1 from both sides. Excuse me, and add the 1. So if we work that out, that's going to give me 6x squared plus 5x plus 1 equals 0. All right, so now we're back to factor. I want to get this down to 2 pieces equaling 0 so we can break that up and solve. All right, so once again, we've got a times c up top, so that's 6 times 1 gives us 6. On the bottom, we have b, which in this case is 5. So we're looking for two numbers that multiply to 6, but add to 5. So that would be 3 and 2. And actually, I'm going to color code these. And that's how we break up our middle term. Plus 1. All right, so working this out. Factor by grouping. First one, we can pull out a 3x, which will leave me with 2x plus 1. And on the second one, we can't factor anything out, but notice what we have here is exactly what we have here. So the way we take care of that is we factor out a positive 1. And now we have our factored expression. So our last step here is to just break this up in terms of two expressions. 2x plus 1 equals 0. And 3x plus 1 equals 0. So if we solve this, we get our first solution of x is equal to negative 1/2. On the right-hand side, subtract over the 1, divide the 3, and we get x is equal to negative 1/3. Now there's one last little piece that we'll have to check in just a second. It's about 95% of the work. There's just one last little thing that, honestly, if you're going through this the first time, you would never think to check. but questions on this from start to finish. Okay, so the one thing we have to check, and it's the one thing that students tend to forget, so do be aware of this, is what we call the domain restrictions. Remember that anytime we have x in a variable, there's always a possibility that we divide by 0, which is undefined. So if we look at this equation, there are certain values that x cannot be. And the way we used to get those is we just set our denominators equal to 0 and solved. Or another way to look at this is if I just set my LCD equal to 0, well, that'll give me 2x equals 0 and 3x minus 1 equals 0. So the numbers x cannot be is if we solve that first one, we get x cannot be 0. And add 1 divides 3, and x cannot be 1/3. So what ends up happening is if these numbers come up for my algebra, even though they might come up as possible solutions, we have to remove them. So we almost have it. Here we have a positive 1/3. Here we have a negative 1/3. In this case, both numbers are okay. Meaning if I check these two, against my domain restriction, none of the numbers in my domain restrictions end up being final solutions. So in this case, we do have two solutions. X is equal to negative 1/2, and x is equal to negative 1/3. Okay, so this is kind of a step I like to do at the very beginning because oftentimes, by this step I mean checking for the domain restrictions. Once students tend to get to the x equals, they're like, okay, I'm done. They put in their answer, they get it wrong. Like, wait, how could I have gotten this wrong? All my algebra is perfect. And the answer is that we have to do this little check for domain restrictions. So technically speaking, you can do it whenever you want. I tend to do it up front, so that way you kind of get in the habit of doing it at the beginning. So hopefully when you get down to these final answers, you remember to check these numbers in green against your domain restrictions. All right, any questions on this? Okay, so we're just gonna do a couple more. Once again, once you've seen the first one, the rest of these look pretty much the same. We're just gonna have some slightly more complicated denominators, but even then, they're not gonna get much worse. Okay, once again, the prompt here is to solve. Okay, first step, LCD. And we really only have two expressions here, x and 3x plus 1. So, looking for our domain restrictions. We've got these two values here of x equals 0 and 3x plus 1 equals 0. So the numbers, my domain restrictions, the numbers x cannot be is x cannot be 0. And if you subtract 1, divide the 3, you get x cannot get negative 1/3. So these are bad points. If these numbers end up being as final solutions, I'll have to remove them. Okay, so now that we have that, we're going to take our LCD. And everything's going to get multiplied through by this LCD. So every term is going to get multiplied through by an x, 3x plus 1. And the goal here, and what should actually happen, is everything should cancel out. All these denominators should go away. So we have 3x plus 1 cancels, and we're just left with a 2x. On your second term, the x's cancel. So we just have 1 times 3x plus 1. You don't necessarily need to write that. I'm just going to write it to show the multiplication. And then here, 3x plus 1, oops, wrong color. 3x plus 1 cancels, so we have minus 6x times x, or minus 6x squared. So doing some distribution here. Now, once again, this is personal preference. We once again have a polynomial, so I'm going to set that polynomial equal to 0 and factor. I like to keep my highest power positive, so even though it would be much easier to just subtract the 2x over in terms of the actual steps, I think it's usually easier to keep your highest power positive. So even though it'd be easier to subtract over the 2x in terms of steps, I'm going to actually move over everything to the other side. So I'm going to go minus 3x to both sides. I'm going to subtract the 1, and I'm going to add over the 6x squared. So on the left-hand side, that's going to give me 6x squared. 2x minus 3x gives me minus x. And then we have minus 1 equals 0. So once again, factoring out a polynomial. So we have a times c is negative 6. My b here is negative 1. So we're looking at 3 and 2. Since my bottom is negative, that means my bigger is negative. So once again, we're going to factor this out. Oops, color coding. 6x squared minus 3x plus 2x minus 1 equals 0. Okay, so factor by grouping again. We'll pull a 3x out of that first term. That'll leave me with 2x minus 1. On this second term here, we can't factor anything out, but what we have here is exactly what we have right there. So remember that the rule of thumb when that happens is we just factor out a positive 1. So I'm left with the factors 2x minus 1 times 3x plus 1 equals 0. Okay, now we just solve and separate. So we've got 2x plus 1 equals 0. 3x plus 1 equals 0. So subtract the 1 and divide the 2. We get our first possible solution. The other side, subtract the 1 and divide the 3. What happened to the 3x in red? So we combined like terms. So the reason why the 3x, what happened to it is the 2x positive and the minus 3x negative, we combine into a common term of negative 1x. Said another way, if I have 2x minus 3x, that's negative, or if you want negative 1x, or just negative x. So we took those two terms and combined them into that term. Okay, last step here is that we want to check against our domain restrictions. These are the numbers that we can't have in my final answer. And if we look, one of them happens to be an answer we got. So we're going to remove that as an answer. We're not going to type that in. Fancy word for this is what's called a extraneous solution. The extraneous, obviously extra. Oh, you're right. I apologize. Yeah, that should have been -1 there. So we have this extraneous solution, which means that the only thing you'll actually put into your final answer here is that x equals +1/2. So this is the case where those domain restrictions did come into play because one of those was my final answer. Alrighty. Oops. Should have zoom out for 1 second. And flip that up. Okay, once again, start to finish, are there any questions? Alrighty. Just gonna go like I said. From here on out, we're just kind of looking at similar beats here. Okay, so once again, terms, we're going to set them up, find an LCD, multiply through. Okay, so just like before, we're going to take LCD here. Technically, this thing is over 1. Some LCD in this case, if we have, we're going to have 3x times x plus 2. So then for the domain restrictions, we're going to have 3x equals 0, x plus 2 equals 0. So we have x cannot be, I should say, 0 and -2. So if those numbers come up with my final solution, they have to be removed. All right. So working this out, we're now going to take all of our terms and multiply through by the LCD, just like before. So as we multiply through, everything gets hit by a 3x, x plus 2, 3x plus 2, 3x, x plus 2. First two terms we cancel out, the x plus 2. So we have, once again, you can multiply this out in your head, but I'm just going to literally write this as, 3x times 4, just to really make it clear where everything's going. On the second term, nothing cancels out. So what I technically have is 2 times 3x times x plus 2. And once again, if you can shortcut some of the stuff in your head, by all means, feel free to. And then on the right-hand side, the 3x cancels. I'm off with 10 times x plus 2. All right, so a little bit of foiling out here and some distributing. So 3x times 4 gives us 12x. 2 times 3, that technically gives us 6x times x plus 2, or if we multiply that out, that gives me 6x squared plus 12x. It's equal to, on the right-hand side, 10x plus 20. Left-hand side. How would you know that those are the domain restrictions? Someone asked in chat. The general rule of thumb is you're always going to take whatever your LCD is and just break each one of those individual parts into 0. And that will always tell you what the domain restriction is. So the nice thing about doing this all together, you find your LCD, is that the domain restrictions follow directly from what the LCD is. You just take each one of these two pieces, set them equal to 0, and when you solve, that will give you what the domain restrictions are. How would you know to do that? The answer is this is me telling you to do that. This is kind of that, like I said, this is kind of a subtle point that flies under the radar, and usually it's probably the most it's the most common mistake on this type of thing, is that there are going to be times where, like we just saw in this last problem, we'll get solutions that end up being domain restrictions we have to remove. So what I'll tend to do is I like to do it up front so I remember to do it. Once you find that LCD, just break each one of those pieces into 0, and once you solve, the numbers you get out of that will be the domain restrictions. Does that make sense? Great. All right, so once again, for the third time today, we got some polynomial stuff here. Let's just write that out. We got 6x squared plus 24x is equal to 10x plus 1. So once again, polynomial equal to 0 and factor. So doing a little bit of work here, I'm going to subtract over the 10x and the 20. So the 6x squared comes down. 24x minus 10x gives us 14x minus 20. You go straight into factoring right now, but remember that if there's something that you can divide into all of your terms, it's always in your best interest to simplify this down. And if I notice, everything here we can divide through by a 2. So give me 3x squared plus 14x, apart 7x, excuse me, once we divide out, minus 10 equals 0. And now we're going to go through and do our factoring. So 3 times negative 10 negative 30. Oops, wrong colors. These I like to do in black. I do the breakouts in blue. Negative 30 and 7. So things that multiply to 30, 5 and 6, 10 and 3 end up being the magical numbers here. And since the bottom is positive, that means my bigger number is positive, which makes my smaller number negative. So breaking up middle term. It's 10x minus 3x minus 10 equals 0. And now we do our factor by grouping. Here we can pull an x out of both terms, which will leave me with 3x plus 10. I can factor out, they both have minuses, so I can factor out a minus 1, which will also leave me with 3x plus 10. So we have 3x plus 10, x minus 1 equals 0. So to a factor, we break each one of our factored terms equal to 0. And then just solve these. So subtract the 10 over and divide the 3. And here we just add over the 1. All right. So once again, we want to make sure, we'll double check this against our domain restrictions. We have negative 10 thirds and positive 1. My domain restrictions were 0 and negative 2. So because there are no domain restrictions here, both of these are acceptable answers. Neither one needs to be removed. Alrighty. Any questions on that? All right. Kind of once again, kind of zoom out. People to kind of write down a little bit. Move that up for a second. All right. We're gonna do one last one of these solving problems. I'll just do it on page. Oh, I just realized we're gonna need way more pages than that. Hold on 1 second. What I did. Just make it even 20 for right now. Let's see if this is gonna crash me. No. Okay, great. All right. Once again, prompt here is solve. And here's what we have. X over x minus 9 minus 7 all over x plus 2 is equal to 2x plus 81 all over x squared minus 7x minus 18. So we want to find our LCD. And in this case, once again, factored, not factored. So just very quickly off to the side, we're just going to do a very, very quick little factoring here. And I mean, you know how this is probably going to break up because we've got -18 and -7. I mean, we can kind of use these as our guides. Oops, excuse me, pardon me. I wanted this. Got one. I think I just erased it accidentally. That's what I cleared accidentally. That should have been a +2 there, not a -2. I think I originally had that when I went to erase something. I got rid of the plus. Yeah. So what we have here is, and here's how I know, because what we're about to get is exactly these values right here, which is we're about to get -9 and +2. And since we have a 1 in front of the x squared, we can go straight to the factored form. Of 2x plus 81 all over. Once again, we can just read these numbers off right off the factoring. So x minus 9, x plus 2. And this is going to be a very common occurrence when you have these sort of things. Whenever you have this kind of trinomial you have to factor, it's always going to break down so that that factors into the two other pieces, because otherwise your LCD gets really, really messy. So I'm actually going to slide this down. We're going to do the LCD bit down here. So we have a pretty easy LCD of x minus 9, x plus 2. All right, once again, doing our little domain restrictions. Restrictions. Which is x minus 9 equals 0 and x plus 2 equals 0. So we get that x cannot be positive 9 and it can't be negative 2. All right, so now once we have all of that, we're once again going to take this down and multiply through by our LCD. And once again, I tend, for the purposes of the notes, I tend to, do this little duplicate function to rewrite this. If you wanted to take it and multiply through just to save yourself some space and some work, I don't need to see you rewrite this equation like 4 times. I'm just kind of doing that for the people who are looking at these notes later, for them to make at least some sense. But what we're looking for, once again, is we're going to multiply everything through by that LCD. Keep the same order, x plus 9, x minus 9, x plus 2. And we're just going to cancel, as always. So x minus 9 goes away. So we have x times x plus 2 minus 7. And if we cancel out here, we have 7 times x minus 9. And on the right-hand side, the right-hand side, everything cancels. So we're just left with 2x plus 1. 81, I should say. All right, so let's see what we got going on here. We have got x times x gives us x squared plus 2x. And then here we have minus 7x minus 63 is equal to 2x minus 81. If we combine our like terms here, we have x squared plus, let's see, what's that going to be? Minus 5x. minus 63 is equal to 2x plus 81. And then we're going to do a little bit of subtracting. So subtract the 2x, subtract the 81. Oops, I apologize. You know what I just realized? Sorry. There we go. I was like, wait, there's one sign error right there, and that's where it was. Yeah, there we go. Now this is going to work out. So we get x squared minus 7x and negative 63 plus 81 gives us a negative 18, which should look very familiar in this problem. It sets up this way. This was the easiest way for me to set this one up, which is we factored this before, right? We literally factored this earlier, but I'll do it one more time for posterity's sake, which is negative 7 and, no, pardon me, negative 9, positive 2. So we're left with x minus 9, x plus 2 equals 0. And then in this case, what we end up getting is x equals 9, x equals negative 2. But those numbers happen to be exactly what my domain restrictions are. So as it turns out, these are both extraneous solutions. They don't work. And since we have no other option, that means that this is no solution or D any. Either one of those is fine. So in the rare case where both your answers or all your answers are domain restrictions, well, there's nothing left that's not an extraneous solution. So in that case, we have no solution. Okay. Questions on this? Anybody? All right. So that's going to be doing it for 7.4 solving equations that have rational functions. Okay. I think here's a good little place to take a little 10-minute break. So I got 5:40. Back at 5:50. So get up, stretch. I will do the same, and I will see you back here in 10 minutes. All right, everybody, welcome back. Okay, 7.5 is going to be a big section. We should be able to finish today, but whatever we don't, we'll just kind of wrap up on Wednesday. We should be able to get through everything we need today. Rational applications and variation. Okay, variation. I'm actually going to start off with the second piece, which is variation, because it's the more confusing one. It is confusing in the setup. The work is actually much easier. But what we're kind of looking at here, when we're talking about variation, we're talking about measuring two variables against each other. So an example would be like if we look at the hours studied. versus your exam score. We would expect to these work in the same direction, which is if you increase the hours you study, you should see an increase in exam score. This is an example of what we call direct variation. So as one goes up, so does the other. That's direct variation. Number of hours binge watching Netflix versus your exam score. So here we'd probably expect the opposite, right? If we're increasing the amount of time I'm binge watching on Netflix, once again, obviously some is fine, but as we increase it more and more and more, we should see a decrease in exam score. So here they're working in opposite directions. As I increase the value of one, I decrease the value of the other. This is what is called inverse variation. Because they work in opposite directions. So what will always end up happening here is either when we're talking about direct or inverse, they're always going to be looking at two variables. You can kind of call them whatever your book chooses to call these X and Y. And if you have direct variation, it's always going to be the case that, and once again, the variables here, which one you label X, which one you label Y, doesn't really matter, but it's always going to be the case that Y is equal to X, where there's some sort of constant for translation, right? It's like every half hour you study is another 5 points on the exam, right? That would be an example of like a translation. So this K kind of represents just a number that tells us what is the relationship between these two values. Inverse variation is the same idea, which is Y is going to be related to X, but since it's inverted, it's going to be the inverse operation, which is instead of multiplying, we're going to be dividing. But we're still going to have this constant number that's multiplying out. So sometimes you also see this written as Y is equal to K over X. So in the context of how do you work one of these out, the goal is always we're going to be given some sort of initial condition. And then from there, we want to work out a secondary condition. And usually this requires two steps, which is one, we need to find what is this number K. And part two is we use K to solve the problem. So let's kind of work an example with this. You studied 2 hours for the exam. You scored 42 points. If you want to score at least an 80 on the next exam, how much should you study, assuming a direct variation? Direct variation. So once again, whatever you call Y and X, or you don't even necessarily have to work, you could call studied H, you could call the points you scored, that's your exam score, S. What you label these really doesn't matter. If you want to call it X and Y, that's fine. I tend to like to use variables that match what we're measuring, just because it makes it really easy to see which ones are which and which ones to plug in. So assuming direct variation, we're saying that H is equal to some unknown number times whatever our score is. So part one is we're going to find our K. So we've been given these two numbers here. At 2 hours, we scored 42 points. We're just going to plug that in. So at 2 hours, we scored 42 points on the exam. And really, this is, like I said, these are very, very easy equations to solve. So all I'm just going to do is just divide by 42. So we get K. If you simplify that down, that becomes 1 over 21. If you want, you could leave this as a decimal. You can convert that into a decimal. I'm just going to leave it as the fraction for right now. I'll save the decimal for the last step. So we found out what the K is. So this is our conversion rate. This says whatever your score is, if you divide it by 21, that's how many hours you need to study to get that score. So part two is to use K. We want to score an 80. So if we plug in K and the score, once again, here's my relationship between the three variables. We now know what K is. We have a score, so we have 1 over 21 times 80 will tell us how many hours we need to study. So technically speaking, here's the actual exact answer. But like I said, this would be a case where we want to actually simplify because 80 over 21 hours is a silly thing to say. So if you work that out, this gives you 3.8. Round that off. Hours. So once again, we were given an initial pair of how many hours led to how many points. And we use that to find kind of this K value, this unknown K value. And then we use K along with the second input, which was this 80, to figure out how many hours to study for that higher score. Okay. Questions on this? Great. Let's look at another one. The number of hours it takes to build a house is inversely proportional to the number of people working. If it takes 5 people 90 hours to build a house, how long will it take if there are 8 people working on the house? Other housing balance is inversely proportional to the number of people working on it. 5 people. Yep, great. So once again, looking for the keyword here. Somewhere in there, you're going to see the word inversely or, inversely or directly. You're always going to see one of those two. Here we said inversely proportional, same thing as inversely variated. So once again, the thing we're measuring is the time, the number of hours. So if you want, we can still call that H. And the number of people working on it. So I'm just going to call that P for people. So since we're inversely proportional, the number of hours is K over the number of people, P. All right, step 1, find K. So we're going to plug in the fact that we know that it takes 5 people 90 hours. So just plugging that in for H and P. So at 90 hours, we have K all over the number of people, which is 5. So technically speaking, we're multiplying, we're solving for K here, which requires multiplying both sides by the LCD here, which is just 5. So that gives that, we cancel out here, so we have that 450 is equal to K. All right, so part 1, we found K. Part 2, we're going to use K. So we now want to know how long will it take if there are 8 people. So we now know what K stands for, 450. But now, instead of dividing this by 5, we're dividing this by 8, and that's going to tell me the number of hours here. So if we work that out, we get that 450 divided by 8 gives us 56.25 hours. All right. Questions on this, anybody? Okay, one more. Sometimes you have both of them, and sometimes it's not presented as a word problem. Sometimes it's just presented using variables. So we'll just do kind of one more. Suppose C varies directly with X, but inversely with the square of Y. If Z equals 10, and X equals 5, and Y equals 1. Find the value of Z. When X equals 12 and Y equals 7. All right, so there's a lot going on, but really if we just take this piece by piece, it's not so bad. We have z varies directly with x, so z is equal to k times x. There's the direct variation. But inversely with the square of y. So inverse means that we're dividing by it, and it doesn't matter, you can put it here or all over. I'm just going to put it over x. And it says inversely with the square of y. So here we have the set of my equation. Z varies directly with x. There's the kx. But inversely with the square of y, which means we're dividing by y squared. All right, so now we have everything we need. So part one, we're going to find the value of k using our first setup here. Z is 10, x is 5, y is 1. So we're just going to take all that and plug that into my equation. So we're going to have 10 is equal to k times x, which is 5, all over 1, technically 1 squared. So we have that 10 is equal to just, well, 5 over 1 squared is just 5 over 1. So that's k times 5. And if we divide over, that gives us that k equals 2. All right, part 2. We're going to use k, so we have these other two values here of 12 and 7, and we want to find z. So z is equal to, what color? We know k is 2 times, we've got x up top, so x is 12, and y squared's on bottom, so we have 7 squared. So that tells us that z is equal to, well, 12 times 2 is 24. All over 7 squared. 7 squared is 49. And then from here, just divide out. And you get 4, I'm guessing, let's go 0.49. Okay. Questions about this, anybody? Alrighty. So that's kind of the variation part. And really, like I said, this is the actual work here is very, very simple algebra. There's not a lot to these. What makes these difficult is just kind of reading the setup. And that's actually true with a lot of, in the next part we're about to work out. It doesn't necessarily have a lot to do with the difficulty of the work. It's the difficulty of the setup and just being able to read what all of this stuff means and translate it. Technically speaking, I didn't give this a name, but whenever you have more than 2 variables here, this is what's called a joint variation. Usually, you're not going to see joint very often. Usually, you're just going to be told, which variable is inverse, which variable is direct. But technically speaking, whenever you have more than one variable, that is called joint variation. I believe some of the YouTube videos attached to the homework talk about joint variation. That's just whenever you have direct and inverse in the same problem. That's all that means. Okay. Questions on this? Anybody? All right. So the other half of this section is what's known as work. Work problems. And here's what we mean by work. These are actually going to be very, very similar to problems we've set up before, which is we're going to set these up using a table. And once again, this is not technically the only way to set this up. Once again, we're setting this up. We're in an algebra class, so when we see, this is when you have a hammer, everything you see looks like a nail. There are other ways to work this problem out. We're in algebra class, so we're going to set up using an algebraic system. There are ways to kind of work this out without algebra, but honestly, I think that there are a lot of ways that students tend to go wrong with this. And the algebra gives us a nice setup that always works out. And this is another one of those questions that tends to pop up on a lot of standardized tests, your LSATs, your GREs. Bob and Cindy are painting a room. Bob alone can do it in 6 hours. And Cindy can do it by herself in 3 hours. If they work together, how long will it take to paint the room? Okay. So a lot of ways that people tend to go wrong with this is they'll do an average of this. But the way to kind of think about this is Cindy working by herself can paint this room in 3 hours. So if Bob does 0 work, the longest this will take is 3 hours. But if Bob is actually contributing, he's going to subtract some time for that. So we should get a time less than 3 hours, because if they're working together, it should take less time than Cindy doing it by herself. So the way to kind of work this out is to kind of work out what is their work rate. Meaning, how fast do they work? And the way to kind of think about this is how much of the room will be done after 1 hour. We're going to break this down in terms of Bob and in terms of Cindy. So the way I kind of think about this is if Bob alone can paint the entire room in 1 hour, that means that after 1 hour, he's completed 1/6 of the room. Whereas Cindy, after 1 hour, has completed 1/3 of the room. And what we've done is we've talked about these guys as a common rate. We've basically reduced them down to here's how much of the room they each paint after an hour. All right, so then we're going to look at the time it takes each one of them, which is the unknown, right? They're working together. We know how long it does separately, but when we say time, we're saying what is the time for them working together? And the answer is I don't know what that is. So we're going to call that, you can call it X, if you want to call it T for time, if you want to call it H for hours, but that's my unknown. But since Bob and Cindy are working this together, when Bob finishes the room, Cindy finishes the room, so the time is going to be the same for both of them, right? Whenever the room's done, they're both done. So as we kind of see, we're setting up this table where we're looking to get what is the final amount of work getting done. And as we've done before, we're going to multiply across, because if we take the rate times the time, that'll tell me how much work has gotten done. So if we multiply across, we're going to have 1/6 x and 1/3 x. Okay. Questions on the setup? All right, so what we usually do is we take these guys and add them up. You know, we've done this before. We did it with the whole system of equations thing. Like, we've done these table methods before. The last kind of key thing and the last kind of thing that's hard to work out is, well, what are we adding up to? And the answer in this case is, well, right now they're painting one room together. So that's what we're equaling. We're going to equal this one room. And now we've set up our equation. Once again, I think this is the hard part. The actual equation work we're going to do here is actually going to be pretty easy. But questions from the sentence to how we set up this table to how we set up the equation. Great. So then multiplying through. So once again, like before, we've got LCDs here. In this case, we have a simple LCD of just 6. So we're going to take all 3 of my terms, just multiply through by 6. So 6 times 1/6 just gives me x. 6 times 1/3 gives me 2x. The right-hand side, we just have 6. And here we have x plus 2x gives us 3x equals 6. Or if we divide out, we get x equals 2. And remember that x stood for the time. So if they work together, they're going to finish this room in 2 hours. Okay, questions on this example, start to finish. All right. One more. So in this case, Bob and Cindy are working together towards a common goal. So that's why these were added together. There are a couple, you have an example in your homework where the things work against each other. How does that work out? It's very, very similar. Oops, that's not what I wanted. I wanted this. Yeah, it'll be a very, very similar setup. All right, so an inlet pipe can fill a tank with water in 8 hours. There is a drain on the tank that can empty the entire tank in 10 hours. If both are left on accidentally, how long will it take to fill the tank? question mark. Okay, so we have a very similar thing, which is we've been given the amount of work it takes in terms of hours. The big difference here is that these are going to work in opposite directions, right? So we've got the inlet pipe and the drain. Oops, inlet and drain. Once again, we're going to break this down in terms of their rate, the time, and the total amount of work that's being done. And once you've seen this trick once, it's very, very simple to follow, right? We're going to do the rate after 1 hour. So the inlet pipe after 1 hour will have filled 1/8 of the tank. Whereas that's a rate, not fate. Whereas the drain will have emptied 1/10 of the tank. Once again, we're going to call this X. And we know it's the same X because, once again, if they're filling the tank, that means it's done for both. So as we multiply, right back to this. So we'll once again multiply this across to get 1/8 X and 1/10 X. The difference here being that these are working in opposite directions. So we're going to subtract that 1/10 X because it's emptying the tank. For every 1/8 of water that the inlet pipe pumps in, that drain empties out 1/10 of that. And once again, well, we're filling the tank, that's 1 tank. All right, so setup's good to go. Same thing as before, we're going to find an LCD in this case. 80 works, but LCD 40 is actually a little bit smaller. All right, so if we multiply across, do a little bit canceling out here. 40 over 8 is going to leave me with a 5, so that's 5x. Minus the 40 and the 10 is going to give me just 4, so that's 4x equals 40. And here's the easiest equation we're going to solve all day. Because 5x minus 4x is just x, so x equals 40, and that's your answer. There's nothing to solve because it's already solved for you. So in total, it'll take 40 hours to fill the tank. Alrighty. Question on this example, anybody? Same kind of basic premise, same basic setup. The only difference here is they're working in opposite directions, so second fraction needs a minus. All right, let's do one more. And this one's going to be very familiar. We're going to do a distance, rate, time. There's just going to be one subtle change that we're dealing with. And the answer is that we're going to have fractions in there. That's going to be the big key difference. A boat can travel 10 miles upstream in the same time it takes to go 15 miles downstream. If the speed of the river is 3 miles an hour, find the speed of the boat. So we've worked this out before. We're going to break this down into a distance, a rate, and a time. Now it's going to break this down in terms of upstream and downstream. So we were given our two distances of 10 for upstream, 15 for downstream. We're looking for the speed of the boat. I'm just going to call that B. And the speed of the river here is 3. So remember that if we're moving upstream, that water is going to slow me down. So that means that it's going to be the boat speed, whatever it is, minus 3 miles an hour. Whereas if we're moving downstream, whatever my boat speed is, the water's going to push me down farther, so we're going to add on those 3 miles an hour. Now for the last bit, this is the one thing we need to remember, is that distance is equal to the rate multiplied by the time. So if we want to find what is in my time column, normally we would multiply across, but instead here, if we're solving for time, we want to say that time is going to be the distance divided by the rate, right? If I have 100 miles to go and I'm doing it at 25 miles an hour and I want to figure out the time, well, you would take 100 divided by 25 would be 4 hours, right? That's what we're doing here. We're just breaking it down in terms of variables. So what we're saying here is that we're going to take the distance of 10 miles divided by the rate, which for our variable was b minus 3. And for the downstream, we're going to take our distance of 15 all over the boat speed of b plus 3. So the last bit is we have these two expressions. How do they relate to each other? And there's one last little line, which is it takes the same amount of time. So because of that, the first time has to equal the second amount of time. And now we have our setup. Once again, this is kind of the hard part, getting from the sentence through the table to our final equation. Questions on that part? Anything about the interpretation or just kind of the breaking it down part? All right, so we worked these out before. We're going to find the LCD. In this case, everything's factored, so I just have an LCD of b minus 3, b plus 3. So once again, just copying this down. We're going to multiply both sides by that LCD. So in the first one, the b minus 3 cancels, and we're left with 10 times b plus 3. On the right-hand side, b plus 3 cancels. Oops, I apologize. I wrote the same number twice here, and that's silly of me. That should have been a 15 there. Excuse me. So we have b plus 3 canceling out on both sides. So we have 15 times b minus 3. All right, and now we're solving. So we got 10b plus 30 is equal to 15b minus 45. And we're just solving a linear equation, so I'm going to subtract over the 10b and add over the 45. So we get that 75 equals 5b, or in total, we divide both sides by 5. We get b equals 15. And remember that b was the speed of the boat, so that boat is 15 miles an hour. That's our speed. Great. So one last little word problem. Once again, it breaks down very, we've done these kind of distance, rate, time problems. Just really the kind of key difference here is that instead of multiplying to get that last column, we're dividing because we're trying to find the time. That's kind of the unknown we're looking for here. So now that we have that, kind of breaks down to one of our little rational equations. Okay, questions on this? Anybody? All right, folks. So a couple things. Remember one more time, this is going to be the end of the material for exam number 2. As always, I'll be posting a study guide. I would give that a look. And I would also recommend going back through 5, 6, and now 7, and seeing if there's any kind of topics you'd like me to cover. What are you afraid I'm going to put on the exam? And as always, I'll bring pre-prepared material. But if you'd like me to work on something specific, then feel free to bring up those questions on Wednesday as we review for the exam in a week. I'll stick around as always if people have any questions. If not, have a lovely night, and I'll see you back here on Wednesday.